Hello, welcome back to my channel. My name is Emma-Adamah. I'm a data engineer and I'll be bringing you content in data engineering, data warehousing, data pipeline building, ETL pipelines, data orchestration, and all of these things. Today I'll be delving into Neo4j and graph databases. This is the first part in my Neo4j series. I'm really excited to bring you this content. I know many people are familiar with relational databases and SQL. I think structuring data in rows and columns is probably the most popular way to structure data, and it's really effective in many scenarios, I would say. But in cases where you have highly interconnected data, or data that I think where there's potential for rapid change sometime in the future and significant changes to the schema, and you need that flexibility, or in cases where retrieving data is more important than storing the data, or in cases where let's say the relationships within data are more important than the data itself. In such cases, you want to think about using graph databases. Graph databases essentially model data in structured format, but in graph structured format, which means it's nodes and the edges. So in a graph, you typically would have the node, which will represent an entity, and then you have other entities as well. And then you have relationships, which are shown by edges. And the edges themselves could have properties as well as the nodes themselves, which give more context about the nodes and the relationships as well. So essentially, the properties are key value pairs. You'd look at them as key and a value. That's like a JSON format, like you're familiar with if you've worked with other data formats, but essentially it's key value pairs. So you could have a person node, for example, and you could have a name, which would be the key, and then you have the person's name. You could have their age, maybe that's 25, that's 35. You could have all the keys and all the values as well. In the context of Neo4j, this is a graph database that's built in Java, essentially, and you have Cypher query language, which is similar to SQL in that it's the language for interacting with Neo4j databases. Cypher, I would say, bears some similarity to SQL in that you have a clause for matching. In SQL, you have that as a select, which is basically like querying specific information from the database. You also have similar syntax like where, the where clause. In Cypher, you have the return statement as well. You have merge. So I think that if you know some SQL, you shouldn't find it too hard to grasp Cypher query. But I think where graph databases excel is in that you can better model real world scenarios, in the sense that in the real world we think about things in terms of relationships and in terms of entities as opposed to rows and columns. So if you had the person table, let's say, that has properties of a person, and then you have a location, and you'd like to find the relationship between a person and where they live, in a relational database you'd have to merge, right? You would have to join, I should say, those two entities. But in the case of graph databases, you would have an entity person and an entity location, and then have a sort of relationship. We could call that lives in, like you can see on the screen, lives in relationship. And there could be properties specific to the lives in relationship. Let's say how long they've lived there can be a property that's specific to the relationship, but it's not specific to the entities themselves. So the person could have their name, their age, the location could have the postal code, the city, the country, etc. So it just helps you think about problems in actual terms, right? In terms of the real world, how things happen in a real setting. So I think they're really, really powerful. They're very popular in social media networks, for example, because you're prioritizing, analyzing the complex relationships between various users. You could think about knowing which mutual friends a user has, or recommending to them similar content like that they viewed before, or that similar friends have viewed as well. So there are lots of things you can be doing with graph databases. Recommendation engines are really popular as well with graph databases. I've built a couple of them in the past, and I will be sharing one with you in subsequent videos. And also I think that graph databases excel when you're prioritizing data retrieval. Because with data retrieval, you're thinking about performance. You want to optimize for performance. So in relational database, obviously, as your data scales, you have to do more complex joins. And the more complex the join, the slower it's going to run, let's say. So you have to think about optimizing for performance when you're scaling your data and when retrieval of data is a priority. So now I'm going to head to my browser and show you how to download the desktop application, whether you're on a Mac or you're on a Windows. You can get the Neo4j application, desktop application, and then we can get hands-on with writing Cypher queries. I'll cover a couple of concepts today, like creating relationships, creating basic nodes, and just matching in a really basic way, I think, and then we can go into more complex concepts later. Okay, so we'll start by downloading Neo4j desktop. Download. I'm on a Mac, so I'll download the Mac version. If you're on a Windows, feel free to type download Neo4j for Windows. It's pretty straightforward. Okay, so once you've clicked download, you should see a form. Just fill out your information here and download. It should be pretty straightforward. Once you have that installed, usually you have the DMG file, or if it's on the Windows, maybe that's the .exe setup. I don't know what that is, but I think that should be the case. Just install that. It's pretty straightforward. No specific settings to be done either, so you should be good. All right. Now, once you have the application installed, you should be able to open it, and then you fall on the home page. If it looks like this, then you've gotten it correctly. Okay, so we can start by starting a new project. Click new project. You can give this any name. I'll just leave that as the default. And we want to create an empty database to run on the local. So you can go to add, you see a plus button here at the right, local DBMS, because this is going to be running on your local computer. So you can click on that, and by default, this runs on port 7687. You can have that changed if you change the config files, but I'm not going to go into that. So I'm just going to create a very simple database called that social media DB, let's say. And you can give this a random password. I think it requires that it's 8 characters. I'll just say root, doesn't matter. And that's going to get created for us. So just give that a few seconds. Okay, looks like that's done. You can definitely start the server here. Okay, usually this comes up, you just click fix configuration, and now that's going to get started. And now I wanted to show you something. Where we created the database earlier, you can see there's another option, remote connection. And remote connection says you could connect to, say, a Docker container, because you can start any database in Docker, like most databases at least. You can get a Docker image and get that all started in Docker and then connect to that using remote connection. You can also set up a fully managed Neo4j database in DB. Companies, I think many companies do that because it's fully managed, as opposed to having their own database set up in Docker, let's say, and deploying that on some cloud platform. You can do that. You can do, for example, set up in Neo4j and Docker, and then deploy that in EC2 or ECS, as the case may be. So it's up to you, really. All right, so it looks like this is active. The database is active. So we can open this in Neo4j browser. That would give us the interactive shell where we can write our Cypher queries. And let's do that. Great. I have a bunch of stuff already done here. I'll just close everything. It should have cleared my history. I thought it would. My apologies. All right, so we can start on a fresh slate. Now, like we saw in Cypher query, match is the keyword that helps us match and query for nodes. So I could type match. Usually I like to check to see if there's any nodes in the database. Let's see if that works. So match n essentially tells us match all the nodes, because a node is represented by these two brackets here, and anything in between would be the node. And that node, or those nodes in this case, are saved in this variable n, and then I can return that variable, return n. So let's run this and see if it works. So as expected, we see no changes, no records, because the database is empty at the moment. So the first thing we're going to learn is how to create a node. How to create a node. And like we said earlier, a node can have properties. So a node is an entity that has some relationship to another node or a couple of other nodes. Now, if you haven't created relationships, the node wouldn't have any relationships. It will just be a standalone entity. But we can just say a node is a standalone entity in a graph model. So in this case, we're going to be building a social media type mini model or mini set of relationships, however you call it. But we're going to be trying to model social media network where you have various entities known as people or users, and these users have relationships with one another. So like friend relationships, acquaintance relationships, etc. So the idea here is a person has a name, they have an age, they have some other characteristics which are common to all people, and in this scenario you would like to keep these properties to get more information or more context about the individual, and also relationships, like we said, have properties. In this case, our relationships wouldn't have any properties because I want to keep things simple just for now. In subsequent videos, I'll be showing you how to include properties for relationships. However, you can just know that relationships should have properties or could have properties. Okay, so I'm going to start by creating our first user. I'll call her Alice. So create statement, create, simply, well, you can liken that to the create keyword in SQL if you're familiar with SQL. And now, because we're creating a node, I'm going to have that as open brackets, and I'll call this Alice. And now we want to introduce the concept of labels. I already talked about labels, and labels help us group similar nodes into a bucket. So we're going to put this in the person bucket, so which says Alice is a person, and we can introduce properties with curly braces. So say her name is obviously Alice, and I'll just put an age just to keep things simple. It's 25. So let's try to create this and see if it works. Okay, so one label, one created node, two properties. That's good. Now to create several nodes, you can comma separate them. I've created Alice, I'll create 4 more users. Same thing, just comma separate the different nodes. Let's run that. That's executed, all right. Now we want to create relationships. Let's say we want to create friend relationships. I'll call the relationship friend. I want to create friend relationships within the different entities we have here. And if you think about it, look, if someone is friends with another person, all we need is one relationship between them. We don't need to have a relationship from the other entity to the first one. It doesn't have to be bidirectional. One directional alone says that that's a friend. So we can assume that's the case here and have one relationship going from, say, Alice to Charlie, which says they're friends, and we could also have one from Charlie back to Alice. However, if Alice is friends with Charlie, then they're friends automatically. So I'm going to introduce that concept, and now once you've started to match a couple of nodes, you can create relationships, because remember that the nodes will be saved in a variable, and then using that variable we can create relationships. Now I've copied this just to save time. So look at what we're doing here. I'm going to remove this just so this isn't confusing. I'll remove the last three. So we're matching Alice based on the name, and then we're matching Bob as well. So this essentially fetches the two nodes, Alice and Bob. Without the create statement, let's see what that returns. Apologies, you have to return A and B. So let's see, we have the two nodes, like you can see here. Now we need to create a relationship. So I'm going to copy this and paste. Great, so create the keyword, and we have the node Alice saved in variable A, friend, that's the relationship, and this is the syntax. You have a hyphen, then you have the relationship in square brackets, and then you have a colon, and you have the name of the relationship, then you have an arrow pointing to the node. So this is one directional, so going from A to B, and this is going from B to A. So let's create that. Right, so two relationships have been created, and now if we match, say we just wanted to match the entire set of nodes. Apologies, my spelling is bad here. Yeah, great, we see the relationships now created. Now I want to create the remainder of the relationships. Let's run that. So match. So usually you have to include a with clause, because you can't possess variables from one query to the other, because then there will be some confusion across match queries. But I'll explain that in subsequent videos. So we're going to run these one after the other. So that's done. And let's take this. Great. Nice. Now I'm going to create another type of relationship as well. So this is called acquaintance. That'll be obviously people who know each other but are not friends. So this is a different type of relationship. And that's between Alice and David, Bob and Eve. This is pretty straightforward because it's the same syntax as the other one, only that the relationship name is different. Let's see. Okay, we have the same problem here, not using the with, so I'm going to cut that out and return. Okay, so we have all relationships created so far. Can just match and return n. And we see a pretty looking graph now. All right, now let's see how we can query. Let's say I wanted to find all Alice's friends. How would I go about this? So think about it. So if I click on Alice, I see that there's relationships obviously from Alice to others. There's acquaintance relationships, there's friend relationships. Now I want specifically her friends. So again, we have the keyword match. That's the way you match nodes. Match, so I'm looking for Alice, right? Alice is a person. And then we can match her name. And her name is Alice, obviously. Alice. So Alice has some relationship, and the friend one is the specific one we're looking for, to another node. Now, so this is sort of generic here because we're saying what are the nodes Alice has a friend relationship to, and we don't care the direction. We don't care if it's from Alice to David or it's from David to Alice, or it's from Alice to Alice, from Alice from Charlie to Alex, basically. So it's independent of the direction. We just want to know that there's a relationship that exists, a friend relationship that exists between them. So you can then return friend. Let's see if that works. So we have Bob and Charlie. Those are the two friends. You can see this in the tabular view as well if you want. You can see this gives us k-value pairs, and that's really good. Let's go back to the graph. So this is an example of what we can do with this. Now let's say we wanted to check for acquaintances in a similar way. Obviously we'll just change this. Let's say we wanted to find Bob's acquaintances. We could switch this to have acquaintance. Should come up for us. Alright, acquaintance. And we can run this. So a single acquaintance, that's Eve. Perfect. Okay, let's say we wanted to have we wanted to query all the mutual friends, all Bob's mutual friends, Bob and Alice's mutual friends, let's say. How would we go about this? So who's a mutual friend? A mutual friend would be a shared friend, right? So we can do something like we query Charlie and we query Alice, and then in the middle we have the shared friend, and we can return that friend. I'll show you what I mean. So we're doing this for Bob and Charlie, for Alice and Charlie, pardon me. So match. Now I'm looking for Alice as a person as usual, and their name is Alice. I always get this wrong, my word. Their name is Alice. So this is Charlie. And you should have a different variable so there are no conflicts. So now let's say there's a relationship, a friend relationship between Alice and some person, right? Let's just give that variable and say mutual friend, and the same relationship is between Charlie and this person. So I need to have here, okay. So if this makes sense, look at what we're doing here. We're saying match Alice and look for Alice's friends. And if those same friends are friends with Charlie, then they are mutual friends, which means they share a mutual friend, if that makes sense. So I'm going to return this mutual or these mutual friends as case may be. Let's run that. Okay, there are no records of the sort. So does that mean that Alice and Charlie don't have any mutual friends? Let's look at that. Eve. So David, there's no relationship between Alice and David. Okay. So let's see one that we can query for to give us a result. So Eve has this friend. So let's do Alice and Eve. Alice and Eve. We should get a result now. Okay, perfect. So Charlie is a mutual friend. Finally, let's try to have everyone with all their friends. Let's try to return that. So match, let's just call this P person. So regardless of their name, we want to have all their friends. To have all their friends. Friend, we should say friends. So friends, I would like to return the names of the friends. So by using the dot, you should be able to grab any of the properties belonging to friends, because friends are people as well, by the way. So a friend is a person, so they'll have the properties that the person label has. So friends.name. Now, since one person can have many friends, I would like to do something called, I think that's collect. That'll help us concatenate all those friends into a list. And just say as friends, something like this. So I should do friend here and put friend here. I think this makes more sense. So let's say I wanted to have p.name as name, and then name, and this friends. So let's see if this works. Perfect. So this looks really good. So we have Alice. Alice has these friends. Now if you see there are duplicates here, you have Charlie, Charlie, Bob, Bob. That's because whenever there's a relationship going from Alice to one node, in this case Charlie, it also comes from Charlie back to Alice, if that makes sense. So basically that means that we're querying without direction here, and that's going to return every instance where there's a friend relationship that exists between one node and the other. So that's why we have, for hard-to friends, we have this as a factor of 2, right? 2 raised to the power 2. And in this case, you always see that it's duplicated. Here's duplicated, here's duplicated, here's duplicated. So that only makes sense. So we should be able to do something like a distinct, I believe. Let's see if that works. What would that be? Let's try to do distinct friend name. Let's see if that works. Okay, great. Now we have that as distinct, and we returned the distinct friends. So no need to repeat the friend names, of course. So I'm going to leave things here, and in the next tutorial we'll delve into aggregations and some of the filtering clauses like the where, like you're familiar with from SQL. And also at the end, probably in the final video, I'll walk you through a real world pipeline that I've created using Neo4j and served through Fast API. I've set up my database in Docker and connected using the remote connection I showed you earlier. I think that's going to be really exciting. Stick around for that. I'll put all of that into my Neo4j series, and you should be able to access everything. Thank you and take care.